Imagine this. You step through a doorway in the present and meet the person you used to be. If you change that life, who was it that ever needed saving? The clock does not merely tick, it chooses a direction, and our lives are chained to that arrow. Time travel fascinates because it leans against the pillars of cause and effect, daring them to bend without breaking. In the next few moments, we will sift myth from mechanism and cinema from physics to see what nature truly permits and what it forbids. Listen for the quiet click where possibility meets constraint. Time travel, in physics, is not a single magic jump, but a relationship between clocks. To travel into the future means allowing your clock to tick more slowly than the clocks of those you leave behind. High speed and strong gravity both stretch the fabric of duration so that less personal time passes for you while more passes for others. This effect, called time dilation, is a measured consequence of relativity, not a cinematic trick. Astronauts, fast particles, and even precise clocks at different altitudes already drift apart in accumulated time by tiny but very real amounts. Traveling into the past is a different creature. It would mean following a path through space-time that loops back to an earlier event, what theorists call a closed time-like curve. Mathematical solutions hint that wormholes or rotating cosmic structures might permit such loops, but they demand extreme conditions and matter with unusual properties that we do not know how to produce or stabilize. Unlike future travel, this backward route remains speculative and collides head-on with the rules of cause and effect. Riding into the future is not fantasy, but a measured quirk of motion. When you move very fast, your personal seconds stretch so that fewer of them pass for you than for those who stayed behind. Particle beams confirm it, as fleeting particles live longer when they speed around a ring. Flights carrying atomic clocks have returned with tiny but clear offsets. Navigation satellites must be corrected, or their maps would drift. Even without rockets, a clock on a mountaintop slips ahead of one at sea level because gravity is weaker aloft and time itself loosens its grip. Gravity offers a second doorway. Near a massive body, time runs slow, so lingering by a dense object lets you leap ahead while the distant world races on. In principle, a ship that cruises just under light speed or orbits close to a black hole could return to find decades gone elsewhere while only months passed on board. The engineering is brutal, but the principle is solid. Speed and gravity reshape duration. Travel to the future is happening already in crumbs all around us, and with enough velocity or depth in a gravity well, those crumbs add up to a meaningful jump. To go backward in time, physics asks for paths that loop through space-time. These are called closed time-like curves, routes that begin in the present and arrive at an earlier event without ever exceeding light speed locally. The most popular doorway is a wormhole, a tunnel that links two distant regions. If one mouth is accelerated or lowered into intense gravity and then brought back, the two mouths can become out of sync. Step in through the late mouth, and you may exit the early one, arriving before you left. Keeping that tunnel open, however, demands a strange ingredient: negative energy. Other blueprints appear in exact solutions of Einstein's equations. A Tipler cylinder, an unimaginably massive rod spinning near light speed, could in theory twist space-time enough to curl world lines into loops, though it seems to require a cylinder of effectively infinite length. The Gödel universe, a rotating cosmos, also admits closed time-like curves, but it conflicts with what we observe about cosmic expansion. Hypothetical cosmic strings, razor-thin defects left from early cosmic phase changes, might create time loops if arranged just so, but their very existence remains unproven. Even if the mathematics permits these curiosities, nature may refuse to build them at scale. Most designs violate ordinary energy conditions, or rely on negative energy that we can sustain only in tiny, fragile amounts. Quantum fields near a would-be time machine appear to erupt with runaway fluctuations, threatening to collapse the device. Stephen Hawking framed this as chronology protection. The universe conspires to preserve cause and effect. Add the engineering burdens, stability, overwhelming energy, and precise control of geometry, and backward time travel remains an elegant, perilous idea, not a working craft. The classic puzzles of time travel probe the hinges of causality. The grandfather paradox imagines preventing the birth of an ancestor, and thus erasing your own path to the past. The contradiction is obvious. Who pulled the trigger of history if you never existed to do it? The bootstrap paradox is subtler. A song, a notebook, or a blueprint is carried back in time and becomes the very source that inspired itself. The object has no original author. It loops without a first cause. Both paradoxes expose the tension between free choice and a timeline that must remain coherent. Two broad resolutions try to keep logic intact. The Novikov self-consistency principle says every event on a time loop must fit together without contradiction. You might attempt to change the past, but slips, coincidences, or constraints always steer outcomes, so the original history survives. In contrast, the many worlds view allows a branch. Your trip lands in a closely matching past that diverges at the moment of interference. You cannot kill your own grandfather, only the grandfather of another branch. Novikov preserves a single locked universe. Many worlds preserves freedom by multiplying paths. Classical physics erects its own barricades. Many space and time geometries that would create closed time-like curves run afoul of the usual energy conditions, the rules that say matter should not behave more strangely than light itself. To hold open a wormhole, or to bend world lines into a loop, calculations tend to demand exotic matter with negative energy density. Negative energy does appear in delicate quantum arrangements, such as the Casimir effect, but only in tiny, fragile amounts, and only for brief intervals. Turning that whisper of a resource into a stable bridge or a controllable time loop would require a precision and a scale far beyond anything we can plausibly engineer. Quantum theory tightens the screws further. Near the mouth of A would-be time machine, quantum fields are predicted to surge, with fluctuations amplifying in a runaway feedback that threatens to collapse the device as soon as it approaches readiness. Light that circles a loop can be blue shifted again and again, pumping energy into the region until the geometry gives way. Stephen Hawking gathered these threads into the chronology protection idea. The universe conspires to preserve cause and effect, allowing the equations to flirt with time loops while arranging physical processes that prevent their birth. On paper, the past can be reached. In practice, deeper laws may keep the door locked. Many myths about time travel grow from half-true headlines. Moving faster than light is often imagined as a shortcut to yesterday, but special relativity warns that superluminal signals would scramble the order of events between observers. That does not grant a steering wheel for causality. It signals a breakdown of the rules that keep cause before effect. The famous tachyon is a proposed particle that would always outrun light, yet no experiment has ever found one. Until evidence appears, tachyons remain a clever algebraic ghost, not a ticket to visit last winter. Quantum buzzwords are easily misunderstood. Quantum teleportation does not beam matter or messages instantaneously. It transfers the state of a system using shared entanglement plus ordinary signals that still travel no faster than light, so the no signaling principle remains intact. Time crystals and ideas of influences that seem to flow backward in certain interpretations of quantum mechanics are intriguing, but they do not assemble a practical time machine. They refine our language about time. They do not let us rewrite it. Modern time physics already powers daily tools. Global positioning satellite networks only work because their onboard clocks are corrected for both speed and gravity, or your map would drift across the street. Atomic clocks set the heartbeat of communication networks, finance timestamps, and scientific instruments. Precision timing lets gravitational observatories sense tiny ripples in space-time and helps geologists weigh the planet's shifting crust. Even consumer cameras and phones lean on relativistic corrections each time they locate you or align time across distant servers. These lessons also shape what information can and cannot do. The ban on contradictions hints at limits on signaling. No message can outrun light or rewrite its own origin story. The arrow of time, tied to entropy, points from a remarkably ordered early cosmos toward ever greater disorder, which is why memories live behind us and not ahead. Philosophically, the stakes are bold. If the Novikov view holds, free choice on a loop becomes choice within a narrow corridor. If many worlds branch, identity itself becomes a river that splits and keeps flowing. Time travel turns out to be stranger and stricter than legend. Moving into the future is not a miracle, but a measured feature of motion and gravity, one we already correct for in our tools. Turning back toward the past lives mostly on the page, where wormholes and rotating geometries beckon, but demand ingredients that nature hides or withholds. Quantum unrest and energy rules rise like guards at the doorway, hinting that the universe prefers its causes to precede their effects and its stories to avoid knots. Yet the allure remains, and it serves a purpose. Physics invites wild imagination and then ties it to careful reasoning, reminding us that wonder and restraint can share a single map. Perhaps the choice is not between fantasy and fact, but between kinds of coherence we are willing to accept. If you could attempt one careful experiment in time travel, which path would you trust more? The self-consistent loop of Novikov, or the branching freedom of the many worlds?